Good morning, class. How's everybody doing today? This is Tim Tomlanovich. Hope you're doing well. Hope everybody's safe. What we're going to go through now is we're going to go through Learning Plan 2. Um, this is the second part of Learning Plan 2. It's something called moments. So we're going to discuss moments. Okay, so moment of a force basically is a moment. Okay, as we look right here. If it works, maybe, maybe not. Okay, right here. Moment equals a force times a perpendicular distance from the line of action. Okay, so if we look at Garfield here, remember F here is the magnitude. F is the magnitude of our force. Okay, the sense is the arrowhead, so it's acting down, so it's negative. Okay, the line of action, remember, is the arrowhead shaft. Okay, so the green dashed line is the line of action, and the point of application would be, if we go right here, is right there, right on that plank. Okay, so the four characteristics of a force. Remember, due to principle of transmissibility, as long as we don't change the magnitude F, the sense, and we stay along the same line of action, which is along the green dotted line, we can move that force around. Okay, so a moment, which is a force, times a perpendicular distance from the line of action. So this is important. Perpendicular distance from the line of action. So would you agree that this is a 90-degree angle, this is a 90-degree angle. So it doesn't matter where I measure it from, to the point of rotation. So basically, if I have a vertical force in the y direction, I need an x distance. If I have a horizontal force, I need a y distance. Okay, so basically it does not matter. So if I project this line, here's my point of rotation. So this force F times my perpendicular distance d to the point of rotation is a moment. Think about it as a wrench. Okay, now in structural analysis, so it can go either way, but for us, typically we assume when it's rotating. So right now, Garfield is going to rotate, would you agree, in a clockwise rotation? Because why? Because what I'm doing is, if I just erase some of this, I'm looking at my sense. Okay? If I look at my sense and it's Garfield is going down, and if I connect a pretend string, if I just do a pretend string to my point of rotation, which way does it want to rotate? So Garfield is going to rotate counterclockwise. So we assume counterclockwise moments are positive. Okay. And then if Garfield moved over to the other side of my point of application, which is right there, basically if Garfield was over here, then we would rotate clockwise. So that is a negative moment. Okay. So clockwise moment. So remember, clockwise moment is negative, and they call this anti-clockwise, or counterclockwise is a positive moment. Okay, so it does. You can actually flip these around as long as it's consistent. It just the engineer, you can decide, but typically in engineering we assume a counterclockwise rotation, a positive moment. So again, a moment is the force times a perpendicular distance to the point of rotation. So find the point of rotation, find my force, extend my line of action, find that perpendicular distance. Again, a vertical force, we need a horizontal distance. A horizontal force, we need a vertical distance. Okay, so a vertical force, a horizontal distance, a horizontal force, a vertical distance. All right. Okay, so again, counterclockwise, positive, clockwise, negative rotation. So this is out of your textbook. So if I look at this little diagram, just think of it as a wrench. So to see this little, let's see if I can highlight that. There we go. See the little T, upside down T, that stands for perpendicular. Okay. So we have a force. So my line of action keeps going, doesn't it? And then my perpendicular distance to my point of rotation, which is the nut. This is my point of rotation. This is my force. So right now, if I pull down on that wrench, which way is it want to rotate? It's rotating counterclockwise, so it's plus. Okay, so dF, F times perpendicular distance. All right, so if we look here, if we want to do the moment about point A here, so we go moment, stands for moment, and this is key, is this little subscript is telling me where I'm rotating all my moments about. Point A. Point A is I am rotating all my forces around point A. So if I look at this little problem here, is my force, the moments about point A equals force, the sum of the forces times the perpendicular distance. So if I look here, I have a force of 3 kips. Okay. And if I look, my sense is pointing down. So here's my point of application of that force. My magnitude is 3 kips. And here's my line of action. Okay. So 3 kips. And which way? I connect the screen, and it's actually going clockwise. So it's a negative rotation. So don't get this confused. Don't get confused that this is a negative force because it's pointing down, right? It's in the negative y axis. Don't get confused rotation versus sense, but we're looking at senses of the forces to determine is it negative or is it positive, or is it negative or a positive rotation. So because I'm looking at the sense, it's telling me I am now rotating clockwise around point A, so it's a negative rotation times my perpendicular distance from my line of action, and they say that is 5 feet. So my moment 3 times 5 equals 15. Now, my units, kip times feet. We're multiplying the kip and we're multiplying the feet. It's not kips per foot, because kips per foot is this. Do not say this, kips per foot. That's what that means. I'm saying I'm dividing the kips and dividing it by feet. So this is kip feet, pound feet, or foot pounds, inch pounds, okay? So it's kind of like a torque. So this answer here is a negative. So the negative is telling me it's a negative rotation because it's going clockwise. Kip feet of rotation. Okay, so that is my answer here when I look here. Now I want to just point out something. What happens if my point of rotation keeps getting closer and closer? What happens if my point of rotation is at the same spot as the point of application? Do I have a perpendicular distance anymore? Do I have, because it's a vertical force, I need a horizontal distance. Is there any horizontal distance from that point anymore? The answer should be 0. No, there's not. So there is no perpendicular distance. So that means there's no moment. So basically, when you hear me say this, if the line of action passes through the point of rotation, the line of action passes through the point of rotation, the moment is 0 because there's no perpendicular distance. Let's use point A as the point of rotation, and then I have another force here, F2. let's just say this force goes like this. It goes up. My line of action, because if I extend my line of action, the line of action passes through the point of rotation. That means there is no perpendicular distance, is there? To point A. So that means the moment is 0. So there's something to keep in mind. All right. Example time. All right. Moment of a force. Example 1. All right. Let's say this car, we have a force acting down right here. This little car, it's a pretty light car, weighs 100 pounds. Here's my, let me start over because we need actual distances. So we have, let's just say it weighs 1,000 pounds here. And then, because a car, gravity acts down, okay? And then we have this weight here, over here. So we have 3 of those, so this weighs 3,000 pounds. So my point of application is here, my sense, my magnitude, my line of action, and I'll draw the line of action in a hidden, see, my line of action is here, my line of action is here, and my point of application here is there. All right, let's get some distance. Let's make this easy for ourselves. So this is, let's say this is 10 feet, 10 feet, 10 feet, 10 feet. All right. My point of rotation, we're going to call that right here. We're going to call that point A. All right. So a moment. So we want to sum the moments about point A. So this is my sum sign. Sum of the moments about point A. And if you want to help you remind yourself, put your sign convention here. So that's telling me that counterclockwise is positive. Remember, this A subscript is telling me what? This is very important that you write this down, because when I check your work, I need to know where I am summing my moments about. And I am summing my moments about point A. So remember, you can sum your moments about anywhere. I can sum them way over here. I can sum them way over here, as long as I know the distance from my line of perpendicular distance from my line of action to that point. All right, so let's do this. Sum of the moments about point A. So it doesn't matter where we start. So we have 1,000 pounds. That is going counterclockwise. So that is a positive force. 1,000 pounds times. So my perpendicular distance all the way to point A from this line of action, 10, 20, 30 times 30 feet. So okay. And now this 3,000 pounds is going, right? If I look, is going clockwise. So that is a negative moment, minus 3,000 pounds. So the minus is telling me it's not minus because my force vector is negative. It's minus because my rotation is negative. Times my perpendicular distance to the point of rotation, which is 10 feet. Okay. I'll grab a calculator here. I should be able to do this in my head, but it's early for me this morning. Times 30 minus 3,000 times 10. Look at that. The answer is my sum of my moments about point A equals 0 foot-pounds. Very interesting, isn't it? So basically, think of this car. This is a wrench. So I look at moments when you're trying to loosen a bolt. The longer the handle, the easier it is because I'm increasing my moment arm distance, which is that perpendicular distance from the line of action. So this 3,000 pound force, these 3 cars, and because my moment arm is so distant, is equaling the same moment as this 1,000 pound force, but it's further away from that point of rotation. So kind of an interesting fact. So that's moment. So why do we need to know this? So believe me, you will need to know this. This will come probably next lesson. I'll explain why you need to understand moments. All right. Moment of force, example 2. All right. So we want to find the moment. Find the moment about point A. Okay. So here's point A. All right. So this is a 200 Newton force. So my line of action is right here. My point of application of this force vector is right there on the end of the wrench. My magnitude is 200 newtons. My sense is negative because it's pointing down. All right, so my perpendicular distance, remember, I need to find this distance right here. So if I'm looking at this, so it doesn't matter where I measure it from. Is this the same distance? Basically, I'm measuring between two parallel lines, D perpendicular, okay? I know this is a 512. Is this a right triangle? So I need to find this leg of this right triangle. My hypotenuse is 1 meter, so I need to find this distance x, okay? So we know we have a 5, 12, 13. So if we do similar triangles, and I'll do this right up here. So here's my big, okay, I know this is 1 meter. I need to find x, okay. My slope triangle, if I do the little guy, I'm just going to flip it around. Basically, I'm going to just flip this around. I know this is 5. This is 13. That's the hypotenuse, right? Because I'm just flipping it. And then this is 12. Okay. Or what can you do? So this angle right here, because this angle right here is also the same angle right there. Just reverse. So I can take the inverse tangent of 5 over 12, right? Or I can do similar triangles. So I need my horizontal distance, which is 12, my horizontal of my slope triangle. See, 12 over 13, okay, times 1 meter, right, over the hypotenuse, and that equals, this is why you need to know trigonometry. So 12 divided by 13 is 0.923, 0.923, 0.923 meters. So now I know my perpendicular distance. Let's do trigonometry. Okay, so theta, I'll make that blue. So theta, this is also theta. The opposite over adjacent is tangent. Inverse tangent of opposite of 5 over 12 equals theta. I'm going to do this 2 ways so we should get the same answer. So 5 divided by 12, and we take the inverse tangent of that answer, and I get 22.62 degrees. 0.62 degrees. All right, so now I know that's 20. So the cosine of 22.62 degrees equals adjacent, which is x, number I'm trying to find that, over my hypotenuse, which is 1. So if I take the cosine of 22.62, I get 0.923 again. Same answer. All right, so now I know my perpendicular distance from the 200 newtons. So, all right, so which way is it rotating? What color should I use here? I haven't used a lot of green. So here's my pointing application. My sense is pointing down. I connect a string to point A. So it is going clockwise, so it's a negative rotation. My force, which is 200 newtons, times my perpendicular distance, which is 0.923 meters. And then I get my moment, so that's my torque, or my moment around. So righty-tighty, I'm actually tightening that, right? Lefty-loosey. Oops, sorry. Just didn't want that to happen. I must have pushed a button. I'm on my laptop right here using a pen. 200 times 0.923. So that equals 184.6. That's negative. Newton times meters, or Newton meters, equals the moment about point A. Okay, so remember, A. So I could move my rotation over here. This is important. I need to know where my rotation is. So I can move it over here, up here, as long as I know distances. So that's that example. All right. I always forget to turn off the automatic save. Now I got to delete all this text on here. All right, moment of force, example 3. Okay. So pretty soon, let's look at this force. Let's look at this force, and I'll go over. We'll go over how this is called a distributed load right here. This little W3 equals. Okay, so basically what this is, these are floor loads, moving ahead a little bit. These are actually next semester, believe it or not, these are floor loads. And then what we need to do is this could be a joist or a beam. What we need to do is actually figure out the resultant, which basically this could be a wall. This is your wall, to figure out how is the load transfer from the floor down to the beam member down to the wall, because that wall has to support it. Okay, so basically what I want to do is I'm just going to do a quick. So basically we take this. We know the center of a rectangle is, the centroid of a rectangle is halfway in between, so 4 feet over. So I just want to show you moments. Okay, so this is 4 feet. So how do I convert? What's the area of a rectangle? It's a height. So the height, this is representing a load, is the height. So 745 pounds per foot times a length, right? So I want to turn that into a point load. So if I just take 745 times 8, the length of my rectangle is 8. So that's 5,960 pounds. Okay, and I do the same thing over here. Center of my rectangle, centroid of my rectangle is half of the distance, which is 6 feet to here. Because that's, why do I need to know it? This is the 6 feet and the 4 feet. Are those my perpendicular distances to a point of rotation? Yes. So I'm turning this into a point. This is a rectangle. My height is 1,465 pounds per foot. So every foot there's a 1,465 pound times my length of my rectangle is 12, and I turn that into a point load, which is 17,580 pounds. Okay. Now, just for this moment example, and we'll revisit this again sometime, I want to take the point of rotation at point B, right here, at point B. Just so you understand, this is just so you understand moments. We use moments to solve problems here, statics problems. All right, so I'm telling you, I want to find the sum of the moments about point B equals, all right, this is my positive rotation. So if I look here, so basically this point load and this point load take the place of this. They call this the distributed load. So those are replaced. So these, we don't want to count them twice. All right. Some of the moments about point B. So if I go from left to right, I have my point of application is right there. My point of application is right there. I know it's 4 feet over here. It's 6 feet from there. My line of actions, right? Here's my line of actions. My magnitude, whoops, sorry. My magnitudes are right there. And my senses, okay? So the moment is a force times a perpendicular distance. So we take this one. This is rotating counterclockwise around point B. So we have 5,960 pounds times my perpendicular distance. Okay, so that is from my line of action all the way to point B. So I know if this is 4 to here, that means it's 4 to here. So 12 plus 4 is 16 feet times 16 feet. Now I'm going to add this moment. This is also going counterclockwise. So that's a positive rotation. So I'm going to add that plus 17,580 pounds times, okay, my perpendicular distance from the point of application, line of action, to the point of rotation. So this is 12. So that means half of 12, that is 6 feet. And then that equals, so if we add that all up, so 5,960 times 16 plus 17,580 times 6, I get 200,840 foot-pounds. So that is the moment at that point. So that is, so when you think about it, this, if you look at these forces, this whole B wants to rotate around B, right? Or if we go around point A, we'll get a different answer because the distances are different. So this is what we need to do, is we need to figure out what's the moments, because this is kind of like a connection right there, you know, a floor joist connected to a wall, okay? Don't worry about these R numbers. We'll discuss that next semester, but I just wanted to explain a moment. So how does that work? So there's another example. All right, let's talk about Varganen's theorem. Varganen's theorem is basically what it says is if we break our force right here, so if this is at any angle, we can assume that's the resultant, that's the hypotenuse of our triangle. If we break it into X and Y, and we sum the moments Fy, horizontal distance, Fx, vertical distance. So if we sum, as you can see here, if we sum these moments, it'll equal the same moment right there. Because reason why we would like to break it into X and Y, because isn't this a little more tricky if we make a right triangle here, and then we got to start doing trigonometry, etc. So, because we need, this is our perpendicular distance from this angled force. So you got to start doing trigonometry. So basically what Varganen's theorem says is this force, the resultant force times this perpendicular distance will equal the same moment of the resultant force breaking up into the X and Y components, or I call them vertical components, and then you sum them up, so the moments will be the same. This makes our life easy when we're trying to do structural analysis. That's what Varganen's theorem is. So obviously, let's do an example. So I'm going to do example 2.15 on page 48. Let me draw the figure out here, then I'll read the problem to you. Let's see, let's use black. All right, I'll read the problem. It says determine a moment MA, see M subscript A, so that means I want to rotate around point A at the base of the buttress due to applied thrust force F. Use Varganen's theorem. Force F is a 512 slope. All right, so if I draw this guy, we have this. We have this. I need to move it over because I have forces. Let's try this again. That's why I have 2 pages here. Let's do this. And let's move it down. I need room. I wish I had my big marker boards in the classroom. That's okay. We'll get her. All right. We have this. We have this. This. And it goes like this. Okay. So this is C. This is A. This is B. This is D. Okay. So we know they're telling us BD is a distance of 5 feet. So that is this distance right there. We know AD, so length AD equals 26 feet. Okay, so obviously they're probably giving me right triangles. Length CA equals 15 feet. All right, and CB equals 24 feet. So we're giving us dimensions. All right, so now our force. We have a force of 13 kips. Okay. So this will be Fy, this will be Fx, right? Okay, so point B is my point of application of the resultant force. My magnitude of my resultant force is 13 kips. My line of action is at a slope triangle of 512. Right, and the line of action is at a slope of 512, magnitude, point of application, and that's all 4. Okay, so we need to, the problem is asking us to find the moments about point A, right there. So we need to, first thing we need to do is break this force up into X and Y, okay? So if I redo this first triangle, the points of, you got to remember when you break them up into your horizontal and vertical components, okay, the point of applications do not change. So this is also Fx, this is also Fy. So my point of application for my Y force and my X force is at point B. It's just depending how you make the triangle. So that's very important because we need to find the point of application because that's where we're measuring the line of action at that point of application. That's how we calculate the distance to our point of rotation, which is point A. So if I look here, my let's see here, let's use blue. So here's my Fy line of action. Here's my Fx line of action. See how I can just project that point? So Fy distance, so D perpendicular Y, so that's for my Fx is what? 24 feet. All right, and then my dx perpendicular for my y force is what? 15 feet. So I already found my perpendicular distances. Now I just need to find fx and fy. All right, so we have our little slope triangle there. We know this is a 5, 12, 13, or first thing you do is you do the Pythagorean theorem, 5 squared plus 12 squared. Take the square root of that, I get 13. So remember, to find my x force is 12 over 13 times 13. My y force is 5 over 13 times 13. Or I could figure out this little tiny little angle right there, inverse tangent of 5 over 12, which is the same as that angle, or you can do trigonometry. So fx equals 12 over 13 times 13. Fy equals 5 over 13 times 13. Okay. All right. So let's get our x and our y force. So with that, so 12 divided by 13 times 13, I get 12 kips. That is fx. 5 divided by 13 equals 0.38 times 13, and I get 5 kips. So remember, 12 kips, 12 kips squared plus 5 kips squared, take the square root of that, it should equal 13 kips. That's a check. All right, so now we know the sum of the moments about point A equals, all right, so let's look at our x force. Which way is it rotating? Our x force, so my line of action is pointing positively to the right. So here's my fx. It is rotating clockwise. Remember, I connect a string to my point. So that is a negative. So negative 12 kips. Okay, that's my x force, so I need a vertical distance. So my perpendicular distance from my x force. So here's my x. See, I'm looking at my senses for rotation is 24 feet. Okay, now y force, that is going counterclockwise, so that's a positive, so I'm just going to put that down here. Plus, so my y is 5 kips times, so here's my y, my perpendicular distance is 15 feet. Okay. So remember this guy right here, here's 15, because my line of action is right there. And that equals, so if I sum those up, so 12 times 24 minus 5 times 15. So I get 213 kip feet. It's a negative, okay, because this number is bigger. So I have a negative 213 kip foot rotation moment equals sum of the moments about point A. So what does that tell me? If this is a retaining wall, so if it's a negative rotation, that means it's rotating clockwise. Do you agree? So that's telling me, so I'm going to do some really big lettering here so we can kind of get to the point here. I'm going to make this really huge. All right. So that's telling me that this 13 kip force right here basically is wanting to rotate this dam. It's actually wanting to push this dam or this retaining wall clockwise because it's a negative rotation. That's not good. This thing's going to tip over. Okay. So this is something for structural engineering. This is why moments are important. So without using Varganen's theorem, so if I just make these really huge, It just got huge. So if I take this, so remember the line of action extends like this, correct? Now I would have to find, this would be, right there, would be my D perpendicular. So I would take the 13 kips times D perpendicular, and I should get the same answer. But does anybody want to do this trigonometry? So you'd have to figure this out. So obviously we know this length, right? We'd have to, we could figure it out, but it's just a lot of trigonometry. That's why it's easier just to break it up into X and Y force. So that's Varganin's theorem. So that's moments. So force times perpendicular distance from the line of action of the force to the point of rotation. Okay? And that is it for examples, and I think we're done. So here's your what am I trying to say here? Your homework. So read pages 42 of 51 of the textbook. That's in chapter 2. Definitely go through the example problems. And then problems 2.14 and 2.17 on page 46 of the textbook and page 220 on page 51. Remember, the solutions manual is in the Blackboard, so you can make sure you're on the right track. I recommend you do more problems than what's stated here. And then remember, Tuesday from 12:30 to 3, I will be on WebEx. I'll be in my office. To chime in if you're not on campus, if you need help. If you're on campus, you want to meet face to face. You just, I'm in BC 106E, so if you just knock on our door, we keep our door locked. Due to FERPA, we can go in our classroom and help you with problems that way too, if you'd like. So thank you, everybody, and hope you have a great day.